Section 10.2 is called exponential functions. An exponential function is just a function where the exponent has a variable. I'll just put S in parentheses in case there's multiple variables. Usually it's just one. Typically, the way that we graph these go ahead and take a look. So if you have a graph of, say, 2 to the x, or 3 to the x, or 4 to the x, or 5 to the x, they look like this. What you would do is you would just pick different x values, make a table, connect the dots, and you would get a graph that looks something like that. Sometimes you might be asked to graph a fraction with a variable. For example, like 1 over 2 to the x. That graph would look similar, it would just be going the other way. It would be reflected over the y-axis. So just like, quadratic graphs look like parabolas, if you have an x in the variable, it's going to look something like this. When I talk about it, there's 3 things that I would like you to remember. Is that the shape is a hockey stick. Also, the y-intercept is equal to 1. The way you get the y-intercept is you just put 0 in for x. Anything to the 0 power is 1. The third thing to keep in mind is what's called the horizontal asymptote. It's just going to be y equals 0. Horizontal asymptote, we've talked a little bit about asymptotes in this class. An asymptote is just a line that a graph gets close to. So these graphs are going to get close to the line y equals 0, but they're not actually going to touch it. Fun fact, if you ever heard of the song Can't Touch This by MC Hammer, it was written about an asymptote. I just made that up. Anyway, my high school class was a little dry today. They were telling me it was a long class, so I did the Irish jig. Every once in a while, I try to spice things up a little bit. Irish jig. I'll show you at the end of the class if you really want to know. All right. So those are what the graphs look like. The domain for these graphs, there is no radical. There's also no fractions. So the domain would be any possible number for both of these graphs. The range is also similar for both of these graphs. I want to take a shot at what that would be. It wouldn't be 0. 0 would be the lowest it would be. It doesn't quite touch 0, and then it goes up for forever. I would write that in interval notation. No. Asymptote is only for log functions. We talked about logs in our last section. That would be a vertical line that the graph doesn't cross. And if you, even though the graph looks like it's going like up, it's like a sharp thing, it actually just keeps growing. Right, so, good question. I wanted to show you how to graph a few of these. The way that we graph is most people graph these by making a table and plotting points. I'm going to show you a little shortcut. So the graph is similar to when we were graphing quadratics. If you had a graph of 2 to the x plus 4 power minus 3, the very last number determines whether you go up or down. So this graph would go down 3. Also, if you take a look at the inside power, it says plus 4. Is that going to the right or to the left? If the inside is plus, to the left. So very, very quickly, we could graph this. This graph looks like a regular 2 to the x graph, but it got moved 4 units to the left and down 3. So what this means is that the horizontal asymptote is usually 0, but now it's moved down 3. So horizontal asymptote would be y is equal to -3. And we could also find the y-intercept. The easiest way to get that is by just putting 0 in for x and solving. That's how you get the y-intercept for any graph. If you put 0 in for x, you get y is equal to 2 to the 0 plus 4 power minus 3. 2 to the 4th is 16. 16 minus 3 is 13. So my graph's a little inaccurate. The graph would actually touch across the y-axis at 13. Your graphs for me don't have to be perfect. As long as it looks like a hockey stick, you have the correct y-intercept and you have the correct horizontal asymptote, everything's good. All right. I do want to just show you how to graph if by making a table. So let's say we had a problem where it's, we'll just do one of these. Let's say you're asked to graph y is equal to 2 to the 4x minus 3 power. This one's a little different. On the final exam, it's a problem like this. That's what you need to know how to do. You can make a table to check your answer, but it also behooves you to know the rules if we're going left, right, up, or down. Okay? So just let's pretend if this is the graph. We'll just make a table, we'll connect the dots and see what it looks like. So we'll make a table for x values. We'll make a table for y values. This graph is not going up or down, so we know the horizontal asymptote is definitely 0. As far as the y-intercept, put 0 in for x, get y is equal to 2, 4 times 0 minus 3. What is 2 to the -3rd power? Anyone remember? We learned about negative exponents. What is it? Yeah, this is the same thing as 1 over 2 to the 3rd, or the y-intercept would just be 1/8. That's something we're going to talk about more in a little bit. The second half of this lesson, we're going to be trying to remember some of those properties of exponents. So the y-intercept is 1/8. Just kind of put a dot around 1/8 or so. We know the graph of 2 to the x is going to look something like this. Remember, if the graph was 1/2 to a power, it would look like that, right? Those are the parent graphs. I told you up over here. If it's a fraction, it starts up on the left. If it's not a fraction, it goes up on the right. But anyway, just to make a table for this, if we pick x values like use -3, use -2, -1, 0, 1, 2, 3. If you were to plug in -3, that y is equal to 2 to to the 4 times -3 minus 3 power. And that would come out to be a really, really small number. It's a 0 with 4 zeros and then a 3 there. Really, really small value. If you were to plug in -2, you would get 0.0004. So not much bigger. And again, you could just type it into your calculator. You don't have to waste time doing that. If you were to plug in -1, 0.0078, so again, a little bit bigger. At 0, it would be 0.125 or 1/8. That's exactly what we figured out before. If you were to plug in 1, you would get 2. If you were to plug in 2, you would get 32. If you were to plug in 3, you get 512. Obviously, this graph shoots up. Looks like it's not doing much of anything. Kind of like my stock portfolio. But then all of a sudden it just shoots up. So it doesn't actually go vertical, but it goes pretty close to it. It just keeps accelerating. Fun fact before we just get to the second half of this section is that Albert Einstein said that the greatest invention of all time is what? Compound interest. He said out of all the inventions, compound interest is the most important, because if you're saving for retirement or if you're investing, you start getting interest on top of your principal, and then you get interest on top of your interest and your principal. And the more time that goes by, the amount in your retirement account, in theory, is an exponential function. People save for retirement. I love talking about that. So at some point, maybe next class, if we have some time, we only have one section to cover, I can go over that if you guys have any interest in it, or you could just go home. But I teach my high schoolers about the importance of saving for retirement early, because the amount of money saved or invested getting interest is an exponential function. About that next class. So to finish up tonight in the 10 minutes or so we have left, I just want to quickly go through how to solve exponential equations. And really, there's just 3 steps or 3 things to keep in mind. One is we want to write both sides with the same base, meaning like 2 to the x is equal to 2 to the 5th. You want to try to have the same base on both sides. And the base is typically a prime number. The smallest prime number is 2, and then 3, 5, he has no prime numbers. Second step is that we simplify exponents. And then the third step is cancel same bases. So like I said before, if 2 to the x is equal to 2 to the 5th, x would just be 5. The trick is figuring out what those bases have to be. Let's take a look at some of these problems. Directions are just going to be to solve. And if you forget some of the properties of exponents, you can go back either in our YouTube videos or in OneNote. The properties for exponents was from, let's see here. We really talked about properties of exponents in section 4.1. Section 4.1, if you're a little rusty on this, section 4.1 had our properties of exponents. assume that you remember that. Let's take a look if we have a problem where it's 25 to the x power is equal to 125. We want to try to write 25, and 125 is the same number raised to a power. So what number can we raise to 25, and what number can we raise to 125? 5, right? We know that 25 is the same thing as just 5 squared. 125 is the same thing as 5 to the third. Using our property of exponents, we multiply the powers if it's power to a power. So 5 to the 2x is equal to 5 to the third. 2x is equal to 3. Simple. That would be 3 halves. Very good benchmark. There's so many ways I can make this harder. One way is by using negative exponents. So let's say if we had 4 to the x power is equal to 1 over 32. 4 to the second is 16. 4 to the third is 64. So we're not going to be raising 4 to a power to get 32. Can anyone think of a prime number we could raise to a power to get 4 or 32? 2, right? 4 is the same thing as just 2 to the second. So instead of 4, I'm going to write 2 to the second. Instead of 32, that's the same thing as 2 to the fifth. We don't want like 2 to the second. We want 2 to a power is equal to 2 to a power. So how can we flip the 1 over 2 to the fifth? If we switch the position, the power becomes negative. Remember we talked about that? So now we have the same bases. So 2x would be negative 5, x would be negative 5 halves. Try one more. What about if we had 9 to the x minus 1 is equal to 27 to the 2x plus 2. We use 5 to a power, we use 2 to a power. Think about what number can you write as a power to get 9 and 27. Great. All right, so this is going to be 3 to the second to the x minus 2 power. 27 is 3 to the third to the 2x plus 2 power. The rest of it is just very easy. We just multiply power to a power. We're going to do 2 times x minus 2 equal to 3 to the 3 times 2x plus 2. This is just very, very simple algebra. Cancel out the bases. 2x minus 4 is equal to 6x plus 6. Putting everything on one side. 10 is equal to 4x. Negative 5 over 2 if you simplify. It works the same way with fractions. Generally, that's how you do it. About 5 minutes. There's one other problem I wanted to show you before we get out of here. You will have a problem like this on the exam. Really, really simple. The problem says the function f of x equals 0.05961 1.004 to the x power. Approximates CO2 in parts per million. Typically, we use ppm to represent parts per million. It doesn't really matter unless you're an engineer or environmental engineer. there's two parts here. The initial CO2 parts per million. And the second part is going to be CO2 parts per million in 2022. I should also just say if X represents years. So when we're talking about initial, that's at the very start. How many years go by at the very beginning before any years of X? Not one. Yeah. If we're starting today and measuring CO2, how many years would go by? None, right? So whenever you hear initial, this just means all this means is that we say X equal 0.05961 times 1.004 to the 0 power. What is anything to the 0 power? 1, very good. So it's just going to be 0.05961 times 1, or 0.05961. Parts per simple. And the last one, it says CO2 in 2022, so the year is X. So simply put 2022 in for X. I do have a calculator. I figured this out. Calculator. I'll tell you what it is. Comes out to be 190.935 parts per million. Those are a little more simple word problems.